Welcome to the APL quest. See APL Wiki for details. Today's quest is the fourth from the 2014 edition of the APL problem solving competition. The idea is that we're given a text and it may have spacing that we don't want. And we want to normalize this in the sense that any trailing spaces, that's spaces at the end of the text, are removed. Any leading spaces, that's spacing spaces at the beginning of the text, are removed. And also, if any words are separated by more than one space, that will be compacted down to be a single space. So let's start with a sample. The basic thing that we want to do here is we want to compare adjacent spaces in order to remove those extra spaces in the middle. And then we need to take care of the spaces at the very end because they might not be adjacent to another space if there's just one space, or rather, if we don't do anything but remove adjacent spaces, then we also reduce the leading and trailing spaces into a single space. But let's get started. So the first thing we want to find out is where are our non-spaces. And then what we can do is we want to make sure to catch also the spaces at the end. So we want to make sure that it's as if the last space is also adjacent to another space. So that would be an extra 0 at the end. And now we can do adjacent, that be a pairwise reduce or a two-wise reduce. And we want to see if any of those are non-spaces. So a space that's next to a non-space is something we'd want to keep. So that gives us this. We can see that we start off with a couple of two spaces, and then we have a space which is adjacent to the T in this, and then we have the four letters of this, and then the first space there is some and then we have the and then we continue on with, and we can see that we have ones for non-spaces and also for the single spaces that are between the words, and then we have the trailing spaces. Okay, now we can use this to filter the text, and that almost solves the problem. Now there are no spaces here at the end because we made sure to add that extra 0 at the end, but there is a problem of a leading space, and we can drop this conditionally. If we know that the text begins with a single space, with one or more spaces, that means we also have to drop one more space that otherwise wasn't caught. So we can easily check that. If a space is equal to the first of the argument text, then we drop it. So this would give 1 if it is. We could also infer it from here just by negating the vector we created here, but this is very, very little work to do. The only real work that we have here is dropping that leading space, because that would mean rewriting everything in memory. So that solves the problem. Let's give this the name A, because we're going to have a lot of different solutions here. Okay. And let's then, for our next solution, take this and generalize it, and while we're making it, also test it, just to see some possibilities. What I mean by generalize it is that instead of taking space as the element that needs to be removed from the beginning and the end, and deduplicated in the middle, we are going to allow you to specify that character as a left argument, and then we can bind space as left argument in order to make it do our specific task. So to make this tacit is actually quite simple, because we're going to put out the space as a left argument, and that means that this different from is just going to be a different from like this, and then we have to, of course, this is becoming a tacit function, not a defen. And the rest of this will just work. This is a dyadic function here. This is a dyadic function here. There's one problem is that replicate or compress here doesn't behave like a function when it is next to another function, the right tag here. But we can fix that with a right tag at top. And then here we have the left argument and the right argument. And that means that we essentially have an equal, except we want to pre-process the right argument of equal with a first. And we can write that just with with the beside the composition. So that's what the entire thing comes out to here. We can try it with our sample text. And that means we can give this a name and just remember to either bind a left argument here, or we could have put a right tag on the right to make it a fork. It'll be interesting maybe to see which one is faster of these two. So let's try that, and at the same time, let's also generate some test data. Now, test data is going to be a bit interesting because we want to try all the different cases that may be with. So there'll always be some internal duplicated spaces, but we also want some with some leading spaces and some with some trailing spaces and all the combinations of that. So how might we do that? Well, and there are different ways we can do it, but let's start by generating some spaces. So we want no spaces and yes spaces, and we can't actually see those, but we can. It helps maybe to do it like this. Right. So we got no spaces and yes spaces, and then we want all the combinations of that. So that'd be an outer product of all of those, and it's still not really going to be very visible here. But now we're going to use these as prefixes and suffixes. So on the left we have the prefixes, and on the right we have the suffixes, and then we're going to have some garbled text in the middle. Let's take 40 overtake on the alphabet. That gives us the alphabet with a bunch of spaces at the end, and then we just want some random numbers there. And let's say just for now for display we're taking 20 reshape 40. So yeah, not very visible. This help. Oops. So typo there. This helps a little bit. Actually, we should probably use display as to see it entirely. So here we can see, yeah, it goes over the edge of the screen, but we can see that we have added spaces in the beginning and the end. But the problem is that our randomness here, it caused us to have some spaces in the beginning that we didn't want to. So how can we make sure that we have a non-space in the beginning and the end? Well, we can just stick an A at the beginning and the end. Right there. And actually, let's turn rows on as well so that we don't run over the edge of the screen, and maybe make these a little bit shorter also so we can see it. There we go. So now we have our test data. We have one that doesn't have any spaces at the beginning and the end, and then we have one that has only beginning, one at the end, one at the beginning and the end, and we can see we're getting some internal spaces here. Of course, in the first three cases, there are no multiple internal spaces because they're very, very short. But we're going to generate giant test data, so that's not a problem. It'll definitely be multiple internal spaces. So that's it. So when we're going to test things for speed comparison, then we'll be testing against all four of these. Copying in the performance comparison from the defense workspace, and then we can run CMPX A on each of these four cases and B on each of these four cases. And we can see the A is somewhat faster, so maybe it wasn't so good to test it after all. Okay, a whole different way of doing this, instead of using this adjacent with the difference from a space, we could also rotate things around, and that gives us so if we compare the Boolean vector with it's rotated by one step, that also gives us this adjacency, but it at the same time allows us to rotate cyclically, and that lets us get rid of having to deal with the edges so especially. So we can try this. Let's take our sample here, and we start off the exact same way. Um, Actually, we can start even making it general. So let's just put it outside. So this gives us our vector of non-spaces, and we have the same thing with adding one at the edge. Now, the important thing that we're going to do next is when we rotate this and one step here, then because we've added a 0 at the beginning, we know that when we rotated one step to the end, we are now getting a 0 at the end instead. So if we now take these two together, so we want the one rotate and also the original, and we can write that like this. Let's actually begin with, well, so we want to combine these two, but let's just stack them on top of each other first. So we can do that with mix at top, comma, over enclose. And we can see these are the two that we're going to combine. So now what we want to do is we want where to preserve anything that is true in either one or the other. So either it is a non-space or it is adjacent to a non-space. So these are the ones we want to keep, and then we just need to do the same thing as before, and remember to stick an attack on top of that slash. Now there's one problem here, that we've added one element, and that means that what we can't just do this compress because it will be a length error. We want to take not the right argument, but rather the concatenation of the space and the right argument. And that gives us this. And because we've added a space on the left, then we need to drop that. And we can do that like this. Okay, let's give this a name. This is going to be C. Don't forget to bind the argument here to the function. So that's one way of doing it cyclically. But there are other ways that we could do it. Let's look at this again. So we can optimize the performance here. There's a problem that we are concatenating, and with a big argument on the right, that's going to be expensive, having to write over the data in memory all again. And we could possibly save ourselves some of this work by working on the Boolean vector over here, removing one element from that, and instead then we don't need to concatenate. We can just take that right argument like this. The only problem is then we are back to so let's we are back to another problem, that we get that space at the beginning if the first element is a space. If it's not, then we don't get a space, because now we're not considering the spaceness or not spaceness of the first element anymore. And the way we can fix that is much like we did before, namely that if space, the left argument, is equal to the first element of the argument, then we drop from there. So that then this works, and let's give that the name D. Okay, but there are plenty of ways to do this. We can also start by the concatenation and go with that. So let's start by having this the left argument here, the space, and then concatenate it in the beginning of the argument, the right argument, the main argument that we were working on. And then we're going to generate a vector, the compression vector for this entire thing. So we can start by saying there which they're different, and then adding a 0 on the front, like we were doing before. We could say give that a name for a mask and then rotate it and then use um, or that. So this would be just a different. It's an explicit version of what we've done before. This is of C, and then we're doing it doing one drop on that. So things look a little bit different when we can assign temporary variables like this. Okay, this is E. And now again, we have a problem that we're concatenating on the left. And we know that that's potentially slow. Concatenating on the right, when the interpreter will reserve additional space for the array to grow, and then it can just write into that space. So that's going to be much cheaper than rewriting the whole thing. So how can we reformulate this to concatenate on the right instead? So we're concatenating here on the right, on the space on the right. And then that just means that we have to move our corresponding 0 over on the right as well. And then similarly we have to rotate the other direction and then dropping from the opposite direction. And there are no more spaces here at the end. So that potentially should be faster. Fs should be faster than E. Okay, there are even more ways we can write it. We've got plenty of ways to write this. So let's start off with again our normal comparison. And now we're adding that space as always. So it's a space indicator in our Boolean vector, so a 0. And then we're going to process that in much the same way as we've done before. We are rotating it one step, and then doing an OR with itself. So far so good. That's the same as what we've been doing before. We're just writing it inline here rather than taking the one outside. But the trick I want to get here is this gives us this. Then we also want to make sure to not catch anything at the beginning. So if we start here with well, I'm going to explain this. This is a test. So these are all fine. But if we have one space here, that's not right because it's adjacent a space adjacent to a non-space, and we want to get rid of that. If we have more spaces, then we start detecting that it's a space adjacent to another space. That's not okay. So a cheap way of fixing this is by saying that any space, any character that appears before the first non-space shouldn't be regarded at all. And of course, any character before the first non-space is going to be a space. And we can do that by taking the running and. Oh, sorry. No, the running or. And because we have our comparison vector here are the non-spaces. So that means we start with zeros for all the spaces, and then we get a 1. So this means as soon as, going from the left, as soon as we hit the first 1, then any character after that will also have a 1. And similarly, any character up to the first one has then a 0. So this is a strict condition. We can then take that and put it up here. That we only want the ones here where we have, remember we have this problem here with this one, if it's also true that it comes after the first one. So now this gives us a good mask that we can work on. And then we just use this to filter our argument. We can try that with S that we had before. Oops, what am I doing wrong here? Oh yeah, of course. We have to drop the drop this 0 from the end after we're done with our logic. Here we go. Alrighty then. We could also use this kind of method of this cumulative or scan to, in a way, spell out all our conditions. So starting with that same vector here, let's spell out our conditions, and then we don't need to worry about this cyclical thing. And the way we're going to spell it out is, again, we're saying that this is the adjacency to a non-space. So it has to be a non-space or adjacent to a non-space, and it also has to come after the first non-space, and it also has to come before the last non-space. So the last non-space, we can write that as a little def in itself. We reverse the argument, and then we do our or scan, and then reverse it back again. So here we've just spelled out with the conditions for keeping a character is that it is adjacent to a non-space, or it's a non-space, and it comes after the first one, and it comes before the last one. Okay. And one final way that we could potentially use this is if we take this the non-spaces as always, and then let's give that a name, the mask, and then we use the less than scan. It's a bit of a tricky one. You kind of have to know this, but what it does is it turns off all ones that appear after the first one. So let's say we have the mask like this. Oh, one second. Yeah, sorry. Here's our mask, and we can see that it leaves only a 1 at the first one, and all other ones in this whole vector are turned off. So that's what we're doing. Now, then we can specify that for something to be preserved, it has to be a non-space, and now what we're going to do is we're going to say a non-space and not. But and not is only, so we could write an and not like this. But and not is only true if this is 1 and this over here is 0. And for Boolean, that just means that it is strictly greater than. So that's a way to write and not. So effectively what happens here is it's exactly the same vector as before, the different from space vector, except that we have forced the first one that's there to become a 0. And now we can use this to cyclically rotate, and that is safe because we know that the first element cannot be a 1. That means that when we rotate it one step, we for sure get a 0 added at the end. And then we can compare that with our mask. Not compare that, I mean combine that with our mask. So it has to be a non-space or adjacent to a non-space as before, but adjacent to does not wrap around. So it looks much like what we had before, but we don't have the problem of wrapping around and messing with the trailing ones. Rather, we're wrapping a 0 around there, and then we can use that to filter it over here. And even if we use something that doesn't have spaces at the end, that it doesn't matter. They're not it does nothing interferes here because they are still adjacent to the non-space that's being rotated one step to the left. nulling that out. Okay, that's I. So now we, for comparison of all these different ways of using the cyclic rotation, um, that were all the letters from C to I. Let's, instead of having to spell those out, let's use another utility from the defense workspace. And it's the generalized iota. Not only does it handle non-numeric data, it also handles a start point and an end point rather than starting always at 1 or 0 if you're using quad 0. So that means that we can write, for example, k to iota g w, and we get all the letters from k to w inclusive. And that means that we can say we want the letters from C, iota G, and we want them all the ones to I. And then we want each one of them concatenated to an each and T. That gives us all the expressions that we want to run, and then we can run cmpx on that. And it's pretty clear that it's our last one here, the clever one that avoids the problem of rotating the wrong data around. That is the fastest one. Good to know. Okay, hey, how about regex? We can pretty much guess that regex is going to be slow, but there are different ways of doing it. They're interesting to see how we could do that. So for a regex solution, um, one way we can do it is by defining exactly which spaces to remove and which spaces to condense. So the ones that need to be removed are in the beginning of our text, any number of spaces, or any number of spaces at the end of the text. The only thing that leaves us is getting rid of the multiple internal spaces. So now we can say once all of those are gone, then we also want to remove any uh, any run of spaces with a single space. We could also say any space followed by any number of spaces, but it's probably not going to make a big difference. So that solves the problem, and let's call that J. Another way we could do it is using a single pattern just to specify all the spaces that need to be removed. So this just moves all of them, replaces with nothing. But what exactly is a space that we want to remove? Well, we can start off like we did before. Any number of spaces in the beginning or any number of spaces at the end. But there's one more possibility. That's the internal spaces that are redundant. What does it mean that they are redundant? It means that they're adjacent to another space, just like we've been using pure APL to do before. So we have a space, and then we want to look ahead and see that there's another space. So if there is another space coming up but not included in this match, then we should remove that space, and that just leaves the last space in every group of spaces. So this solves our problem as well. And finally, we can make a solution where I call it like exception pattern solution. And that's when I start off by protecting certain things in that I replace them with themselves, and then anything that's left over using a different pattern and is then changed. So what we want to keep, those are spaces that are in between two non-spaces. So how can we do that? Well, we could use a look behind and a look ahead, but that it doesn't really matter. And so if we have a non-space followed by a space followed and an upcoming, so that's a look ahead, any number of characters. So the problem here is that uh, this could be the last character, the last letter in our text, and it will be followed by a space, and then we say any number of characters that come after that, that will also match that there should that a space at the very end. So we don't want to keep that. So we need to make sure that something follows and after, and we can't consume a non-space because we might have non-space space non-space space, and we need that middle non-space to be used to justify both of the spaces that are adjacent to it. But what we can say is that follows any number of characters. Look ahead. And then there is something somewhere after that, which is also a non-space. And then, uh, and those are the spaces we want to preserve. Any other space we want to remove. Let's just try this out like that. Um, we could also say that. Well, you might think that we could also say that that we want any non-space followed by space by any non-space. But that would only preserve those places that are just a single space. But we don't want that. We want to preserve one of each of the spaces that are in sequences of spaces as well. But so this is another way of doing it with regex. So three different ways of doing it. The first one was um, to do two different patterns that do the two transformations, leading, trailing, and then separately treat multiple spaces and make them one. There's the one where we are specifying exactly which spaces to be removed using well, it's an OR and three different patterns. And then there's this one where we are exempting the spaces that we want to keep and then removing all other spaces. So let's try that. We want J each of K each of T and K each of T and L each of T. Three different ways of doing regex, and to see which one is faster in our case. Well, yeah, pretty clear that using the two transformations would be faster in our case. This might not be true in every case. Okay, now here's a fun thing. Because of our problem being very specific, we're only dealing with spaces and non-spaces, and we want to get rid of any runs of spaces other than them being a single space inserted there, then we can use a little trick, and that is using the classic way of splitting on spaces or on any other character really. So we partition by where we have non-spaces. And because non-spaces are indicated by zeros, and any element that corresponds to a zero is removed when we're using partition, that means that all the spaces are removed, leading, trailing all the internal ones. Now we remove too much because we want to have exactly one space between each word. But that's not so bad because what we can do then is join with spaces. We could write that as the left argument followed by a space followed by the right argument. But this will fail if we have an empty vector, because that will need the identity element for this function for which there isn't one, because, well, firstly, APL can't figure it out for non-primitive functions, but secondly, there is no argument you can give to this on one side so that we preserve the argument from the other side because it always adds a single space. So we can see we get an error there. Instead, what we can do is we can just add a space to each one. And we know that it's probably faster to add things on the right. So instead of just doing this space concatenated to each one, we'll bind the space on the right side of concatenation. So this just adds a trailing space to each one. We could also use commute for this, but this will work. Oops. Yeah, we should use our sample, of course. And now we just need to flatten it all down and then we have a trailing space that comes out here, and we just need, because we added a space to each one, so we uh, drop the last one. We know that's going to be a space. And that gives us our result right there. So this is one way to split and join. Did I give a name? I didn't give a name to this one. This should be good. And well, it's not really valid, but it would be interesting to see if there's a difference in speed as well between join on spaces and add a space to each one, and then flatten it all out and removing one. So we can still compare them even if we know that it's not really valid. Should be. Yeah. Okay. Should really be the other way around the alphabet there. Yeah, let's fix that. Okay. Fine. Let's try to generalize this a little bit. That's really trivial. If we take this one, then we can just use the left argument here and a left argument here. So that would be a generalization of it, just to show how we can do that. So this is actually a kind of useful thing to be able to bind an argument with a function. That's just what I want to demonstrate. But this form also has an additional benefit that it is extremely amenable to becoming tacit. Okay, so how might we write this as in tacit form? Well, this is just an application between the arguments, and this is the right argument. So we could write this as a right tag here. But since we're just flipping the arguments of the partition and we have a single primitive over here, then there's no point in writing it like that. So we can just, in flipping them around, so we can write that in the proper order. And now we want to add the left argument concatenated on each, but flipped around. And then we flatten this. And then we okay, we need to change our braces to parentheses. And then we could combine this. So because this is a monadic function, so we're just pre-processing the right argument to the -1. But instead of that, we can actually just let it be a final top here. So we have this fork here, which has a fork right argument, right tine, and then a single function, so that's on the top, and then you can just state the -1 drop outside as well. So saves us from this somewhat awkward what do you call it, composition of it. So we can try this, and this works as well in a tested form. So these were all based on splitting and joining. Let's compare them with each other. So let's do this was M to G P, and each one is with an enclosed and each of T. So these are all the split and join. They're probably not going to be fast, but we can still compare them with each other. Oh, something is wrong here in what I've been doing. Oh yeah, of course. The reason it's wrong is of course it's not actually wrong. The problem is it? Hold on. M on S. Oh, M is missing something. M is up here. Join on these. Hmm, what did I mess up here? Oh, this looks right. We join on this on the sample. Oh, of course. Yeah, silly of me. We're doing a reduction here, so we should so this becomes an enclosed. That's what it's trying to show us here with the extra space. It's been enclosed, so we need to disclose that, of course. There we go. That's M. Okay, so this is a good feature of CMPX that it indicates that an element and a result is different from the other results. Okay, now they match each other, and now we can see that first one was very slow. That's the one that's doing the reduction, and it wasn't completely right anyway because it couldn't handle the empty argument, so that's good. And the other ones are much faster than that. Finally, a function that's often overlooked is the find function. The find function um, indicates the beginning of any subarray in an array. So we've got our S here, and then we can say we want to find places where we have doubled spaces. So we can see that we have three spaces at the beginning, and that means there are two instances of double spaces here. There's a double space over here, and then there are all the trailing spaces that cause uh, double spaces at the end. And we can use this. So let's start off with something that just like we've been doing it before. Different from space, and then we're going to do something like that. And then so here when we have different space, we want to look at places where we got 0, 0. So this corresponds to uh, where to what we're doing over here. We just do it using it on the Boolean instead of using it directly on our text. Okay, now we'll come back to this. Let's just do the basic thing first, which is going to be that we want to make sure that so this will this thing will take care of the double spaces eventually. We can see that already here. So if we negate this, then that indicates all the places except for a space that is followed by another space, which are the redundant spaces. So if we use this already to compress here, that gets rid of all our double spaces, but doesn't get rid of our leading and trailing spaces other than compressing them down to become single spaces. But we can fix this. Um, Leading and trailing spaces we can get rid of by with the same method we did before with the scan. So we want to find anything that follows the first one, but not anything before that, and anything that comes before the last one. So we can we can do this reversal, and then we do an OR on that, and then we do uh, reversal again. And that gives us a mask show indicating ones all the way up until the very last one, and that takes care of all the training spaces. And then we can combine it with a regular OR scan. So we want both of these to be true. It has to be true that it's after the first one and before the last one. Oops. Yeah, we need to bind these together as well. So because this is a monetic, so we need to we do that by pre-processing the right argument to AND, and that gives us the internals there. And then the only thing we want to also be true is that it isn't a space which is followed by another space. Oops, we forgot to bind the argument to that. And oh yeah, this is wrong anyway because we want this has to be false. It has to be not a space that's next to another space, and this has to be true. It has to be in the internal part. So it's like the and not, but backwards. So this has to be on the right, has to be greater than what's on the left. And that gives us our mask, and then we can use that to filter the argument, and that gives us our result. We call that Q. Okay. Another idea we can use, now that we know how to take care of duplicate spaces, then we are free to explore other ways of getting rid of leading and trailing spaces. And now there's this thing called idiom recognition, where certain phrases are not actually taken at face value, but are um, interpreted as a single kind of, are seen as a single token, and then the interpreter internally uses a very fast algorithm for doing the same work that this function would have done. And one of them is actually exactly this, to remove spaces. Apparently that's something APLers do a lot, and they want uh, to run fast. So if we type this up, notice that it turned a different color here. That is indicating that this is an idiom and therefore going to run very fast. The problem is, of course, this only removes leading spaces. This is exactly that mask on the leading non-spaces. Um, and we also want to do it from the reverse. But we can do that simply by um, reversing our argument and then applying this, which removes leading spaces, and then reversing it again back again to how it was before and removing the leading spaces, meaning that this whole thing just has to run twice. Um, And once that's done, so we can try this on our sample, so this gets rid of all leading and trailing spaces, then we can apply atop that um, this exact method that we had before. We want the argument where it is not true that we have adjacent a space that's adjacent to another space on its right. That gets rid of that. So this may be fast because we're using this idiom for the leading and trailing spaces, even though we're using find for the middle spaces that need to be removed. Let's call this R. And then finally, let's try to use a bit work with find straight on the bit mask in a bit different way. What we're going to do here is we're going to start for once with things that are spaces. So this is exactly the opposite of what we did before. But the good thing about it is that we can then do an AND scan that gives us all the leading spaces, and then we can do the 1-1 find that gives us all the duplicated spaces, and we don't want any of those, so neither this nor that. We can try this. In fact, let's put it in here. That's what we're going to do. So, um, so all of the leading spaces were removed, and now we only have training spaces. It's a little bit hard to see that we've got training spaces here, but if we use display, then we can see that we've got a training space. There'll only ever be one training space because we have reduced any runs of spaces to a single space. That means that the only thing we need to do is remove a trailing element, which is a very fast operation, if uh, the last character of our input is a space. So how can we find the last character of the input? Well, if we reverse it and then take the first, that's the last, and then we need to drop one if that's true. So that since it's from the end, we can do negate on top of that. Now, this might be a bit faster if we allow the interpreter to use its idiom like this, but we can't do that when it's tested. So let's just write it like this instead, and now it should be able to recognize it as an. That's interesting. It's not written It thinks it's not an idiom when there's an adjacent space. Seems like a bug in the syntax color. Okay, so this finds the trailing space, and just do a bit of tech here just to be. Oh, so interesting. Okay, it wants a space there. Oh well, this should be fast anyway. So if we have the last element being in this vector of indicating where there are spaces, then we negate that. If it's a zero, it just stays zero, and then we drop that many elements on the right. And that should, we can try with display here. We can see that there are no spaces at the end. And we'll call this S. And then we are ready to test our find-based methods. So this is CMPX, and we've got Q each on T, and R each on T, and S each on T. And we can see that R is by far the fastest one of these. Which one was R? That was the one where we were using the idioms to remove leading and trailing spaces. So that's interesting to know. Okay, so in each category, we found out which one was the fastest one. And if I recall correctly, those were A from the category um, of adjacent characters. It was I from the cyclical rotation. We can have a look at them. It was K from the regex. It was P from where we're splitting and joining. And now we had R here where we are using find. So that's these. We'll take these and compare them to each other. Whoops, missing a comma there. And that shows us that A and I are fastest, but they're so close to each other that it's kind of hard to decide when it's being drowned out by other things. So let's try to just do these two. And turns out that A, our very first solution, is actually the fastest one. Very nice. Thank you so much for watching.